take his place when he dies.
Yeah. Some PhD dude will come up. He's like new age. I've Googled myself a couple times.
For my name, it's Black Arizona.
Yeah.
You didn't take him out. Like, there's only enough room for one.
Could you kind enough to circle this and turn it in so I don't have to...
I don't know if he's
Stage in this Aria.
Love him first, by the way.
Yeah, I figured since you guys are dressing down, I have an excuse to not wear yoga pants.
Down, excuse me. I just see my
You look fabulous.
You
want a solution?
He's written
Oh,
books
sure.
focused on Egyptian sacred.
Thank you.
Is what comes up when you Google.
Are you going to the gas party today?
Sacred geometry and pyramid.
I'm sure broken. No, not broken.
Simple patterns, vectors, is also known
Camille.
as rotating method of drawing the geometry.
Oh, no, I...
What are you wearing?
I
I
was
was
Jimmy
tux.
Jones.
Niall,
First division
I'm just going to wear a blazer.
That was today. That was...
Is it good? I have.
Guys, are we going to the Gatsby thing tonight?
Yeah.
Are we? Yeah.
What?
I don't have a tux with me.
You don't have to dress up. You just dress up.
What time
No,
is it?
it's like
Yeah,
They're throwing
Do you have a cardigan?
but like if you just go on.
You have a cardigan?
I'm good.
The cardigans were big in the...
I would never wear
I'll look
a
at
cardigan.
Should be what you're wearing.
In the entrance.
Wait, I have to dress up.
You don't
Just draw a bow tie on your shirt with a Sharpie and they'll let you in.
Emily, are you
Except for you're nowhere near another
I don't know if I'm going. If I am, I don't have anything to wear.
What? You don't have to. You're just watching a movie.
I actually have a
Alright,
Gatsby
then
t-shirt
I'm
everywhere. We made it with my cousin. It's like our party was downstairs.
Okay, let's see. I wanted to answer Mr. Flanagan's question a little bit better. The concern was the distinction between doubling the speed and doubling the momentum. It seemed like it was the same thing, right? If the mass is held fixed, then doubling the momentum doesn't mean the same thing as doubling the speed, and doubling the speed the same thing as doubling the momentum. Well, that's true only in a very limited way, and so I wanted to help you to understand the distinction again between a cause and an effect. The momentum is the measure of the cause, and the speed is the measure of the effect, the rate of change of place. So we have this, notice here, by the way, that the computer is not working, so I'm trying to use this projected document camera here, so help me if you can't see what I'm writing here or if it's not clear enough. So this I'm new to. Hopefully this will work. And hopefully this pen is dark enough. So we have for a massive body, V equals P over M. Is that readable? Okay. Now this is the relationship between the velocity and the momentum under ordinary circumstances, but it's not correct. It's actually wrong in some sense. As we will see when it's not wrong in the sense that the speed is the result of the momentum. That's right. But the particular relationship between the measures is not precisely correct. The deviation we don't see until we get to very high speeds. We get close to the speed of light. When we get to Chapter 10, at the end of this term, you will see that this should be replaced. Rather than having the kinetic energy be p squared over 2m or 1/2 mv squared, and rather than having the velocity be p over m.
It's just the door.
Look at his eyes.
Yeah.
Oh, Mr. Avery! Big surprise. All right. Rather than having that, we will have a more general relationship here. I'm going to write this down. I don't expect you to follow this. I'm just trying to help you to understand the point here. The velocity as a function of the momentum will look like that. So the result is that it's no longer true. If you double the speed, if you double the momentum, you've doubled the speed. In fact, as the momentum gets large, the speed starts tapering off. You can't exceed the speed of light. So you get to a point where you double the momentum again and again and again. The speed is in fact asymptoting out at the speed of light, the speed of a massive body. So it's not true, generally speaking. This relationship that we have in mind here is not generally true. And in fact, there's no reason why it should be generally true, because the momentum is not the velocity. They're not the same thing, right? And so you don't expect necessarily a simple relationship between them. It's a contingent thing. We have to go and make the measurements to find out what is the relationship between the cause and the effect. It just happens that at normal conditions around here where things aren't moving very fast, that the speed is proportional to the momentum. Mr. Frank.
So at a normal speed, in that formula, the C would be so large that the bottom would just be like MC, because the P would be so much smaller it wouldn't even make a difference.
Well, if you want to work through this, yeah. So at low speeds, small p, this is going to be Cp over m naught c, and so this is just p over m.
Okay.
Where m naught is the rest mass. It's the mass that is seen for the body at rest, and the mass actually changes some, but in any case, we'll talk about rest mass. So this would be for low p, and for high p, the p is much bigger than m naught c, and so you actually get the velocity goes up to c. The p's cancel. Cp over p. So the asymptotic velocity, the asymptotic speed is v. So it's not true at high, if it's got a lot of momentum, that if you double the momentum again, it's going to have twice as much speed. It's going to be asymptoting out at the speed of light. The same thing, so a similar relationship is true for the kinetic energy, which looks like this as a function of momentum. It's no longer p squared over 2m. Pardon?
You're going to have to pay for that. You didn't see that.
Thank you. Raise it up. Okay, so the kinetic energy is no longer this p squared over 2m. It's this thing, more complicated. That's right. That's, I guess, okay. Actually, I need to subtract off m naught c squared from this. Yeah, that's what I need to do. Okay, so it's more, again, not a simple relationship. If I double momentum, doesn't double the kinetic energy, except if I don't have much momentum to begin with. If I get a lot of momentum in the extreme limit for high momentum, the kinetic energy goes like Pc is proportional to P. And if I double the momentum, I double the kinetic energy, rather than quadrupling it at low. So this is at high momentum. Okay, but I'm not really trying to get you to focus specifically on a second set of rules or something that we need to understand. I'm trying to disconnect in your mind the cause and the effect and make the distinction in your mind and try to help you focus on that distinction. The cause and the effect are not the same, and it's a little bit confusing in this case because the cause and the effect are so simply proportional to each other. The speed is just proportional to the momentum, and you might confuse them and say, well, they're the same. They're only the same in effect, but they're not the same if you're focusing on the cause and the relation between the cause and the effect. And so I show you another example which relates to a massive body traveling at high speed, already with a lot of momentum, that shows if you double the momentum, you don't double the velocity. If you double the momentum, you don't quadruple the kinetic energy. It just doesn't do that. Okay, does that help a little bit?
Yes.
By giving you a counterexample, I'm trying to broaden your thinking. They're different. Momentum is the measure of the cause, and the velocity is the measure of the effect. And they really aren't. There's no reason to expect that they're going to be simply proportional to each other. It's really rather amazing that under the circumstances around here on the Earth, it is such a simple relationship. Okay. All right, so I was hoping that would be a better answer for you to help clarify what I was trying to say when you asked that question before. In fact, you could go back and redo that problem again with these relations, and you would see that it's something much more complicated, right? It's doubling the velocity is not the same thing as doubling the momentum. Kinetic energy changes in a different way in those two situations. Yes, sir. Mr. Kelly.
Where does E equals mc squared?
Yeah, we'll get there. That's chapter 10.
So where does that?
I'll show you. When we get to chapter 10, you'll see it. We've got a lot of stuff to do today because y'all have a test on Monday on the materials up through chapter 4. The emphasis will be on forces. The emphasis on the test is on forces, but everything from chapter 1 to chapter 4 is fair game for the material. And that quiz, I hope, will get you to renew your memorization. All of that stuff is fair game on this test coming up. What is a force? That sort of stuff, right? Mr. Avery, is this about the test on Monday?
It's about a question about momentum.
Okay.
All right, so I was riding the longboard, right, and I got down the hill, and it got to the point when I had like a few things before it, like stairs, so I had to stop. So when I jump off the board, like, would the board go faster than me, or would it go at the same speed?
Right, good question. So isn't that like the dump truck dumping the sand out of the bottom? Isn't that similar?
Yeah.
So or the airplane dropping the bomb out the bottom, or if you could say you're up on a rail car that's moving and you simply jump up. If you jump vertically, then there is no force acting on the board in the horizontal direction. There's only a force in the vertical direction. So its horizontal impetus will remain unchanged. And it has, in proportion, remember that for a system, the momentum of a part is in proportion to the mass of that part, fraction of the mass. So in that case, the skateboard has some small fraction of the total, but it will retain that when you jump off, as long as you don't kick it forward or kick it back when you jump off, right?
So when I jump off, I could be able to just like stop it right then.
If you do it carefully.
So I wouldn't need to speed up or anything.
Well,
if I'm keeping the same speed.
If you're jumping up off of the board, if you jump vertically off of the board, then both of you should continue moving forward with your same impetus, right? So in principle, you should be able to leap off the board and then land back on the board over here. That should be possible. As long as you jump straight up, you and the board will continue moving forward with the same impetus that you had. Same speed, therefore. And you'll land back on top of the board. Now you can tell if you try that you have to be very careful not to give you or it some backward or forward impetus, because then you'll land somewhere else, right? So, okay, so when you jump off, it is certainly possible for you to kick it back a little bit and you would end up in front of it, or kick it forward and you would end up behind it. So if you're trying to stop yourself, you still have to find some way to drain your forward impetus. How are you going to do that? You're going to, the board's not going to be a very effective means of slowing you down because it doesn't have much mass, right? It doesn't have much impetus to. So you'll have to jump off and land on the ground and use the friction of your shoes with the ground to slow you down. So the friction will drain the impetus, your forward impetus. But the skateboard doesn't have that, so it'll keep going. The only way that you can keep the skateboard from going down the steps.
Oh, board comes first. I first. I was just saying.
Well, in that case, you should kick it back really hard.
And you would go flying for it.
Well, you'll have the same additional. So if the board.
Balance on one foot and you drag your
Oh heck no! I'd be wearing nice shoes.
Oh, okay. Boards and shoes come first.
Boards and shoes.
Boards and shoes come first. Yeah.
You just heel drag, it slows you down and you become.
Alright, and another thing.
That's the thing. That's what you need to do. You just need to fall backwards off the board and just drag the whole thing to a stop, right? Then that'll be fine, no problem. Or you could just stick your shoe off the back and just. Oh, I'm sorry, the shoe. We can't leave the shoe. No, the shoe's got to be safe. So just.
I can use some big shoes.
All right. So let's go forward now. The worksheet that you just turned in on static friction and kinetic friction, and a couple of questions after that, and then I want to prep you for the homework on Wednesday, unless there are any other questions about chapter 4. Let me do one quick thing here for chapter 4. Two kinds of linear motion that we have studied. Doesn't mean that there are only two kinds of motion. It just means two specific kinds of motion. The linear motion we have studied: uniform linear translation, uniform linear acceleration. I want you to write down the generic position versus time relation for these two cases. Uniform linear translation, uniform linear acceleration. So, in the uniform linear translation, what kind of function is it?
Linear.
It's a linear function. In fact, we call it a linear function because the graph is a straight line, right? Position versus time is a straight line. So, x naught plus v naught t, and if we plot that x versus t, it's a straight line, like that, where this is x naught has a slope of v naught. Okay, uniform linear acceleration, what kind of relation is that?
Quadratic.
It's quadratic. And this is true only if a is a constant, right? Doesn't change in time. That's what we mean by uniform linear acceleration, is that the acceleration itself does not change. And if we plot that as a function of time, it will look like, well, depending on the circumstances, it could, if a, let me write it for the case where a is negative. A is less than 0, so it's a deceleration. That would be, for example, the projectile. If x is the vertical motion, a is less than 0. If a is greater than 0, it's going to be curving upward like that. Okay, so this should be, you should have this down. The equation of Newton's law for the uniform linear translation is x double dot, mx double dot is 0, right? There's no net force acting on the body. And for uniform linear acceleration, mx double dot should equal to ma. That is the right-hand side is not 0, it's something else. But it's constant. A is a constant. A and m are constants. And so we can, in fact, drop the mass from both sides here like that. Okay, you should have this down. This should be something you can get down easily, do this, and remember these things. Mr. Flanagan.
On the test, you want us to dimensionally analyze whenever
I will give extra credit for dimensional analysis of your solutions. If I ask you how long does it take to come to stop or something, and then you, so you've got all these no numbers, just a bunch of symbols. I want you to do a dimensional analysis to make sure it has the dimensions of distance or time or whatever it should have. Yes, extra credit for that. Extra credit also for doing checks against simple cases. You know, like the cannon, for example. What answer do you expect for the range if you point it straight up? Well, you expect the range to be 0, right? So you should be able to make simple cases like that where you know the answer easily. Check it against that. Check your result. That would be a good thing. So extra credit for both of those, always on tests, when it's appropriate, you know, when you have a problem like that. Okay, so now let's look at the case of static friction. Now we're moving into friction, conservative forces and non-conservative forces. Let's look at this problem here. We have a mass that's suspended from a pulley, and the other end of the rope is connected to another mass. We have two masses in the problem. And the first mass is resting on sandpaper, so there's static friction that's present. It's not sliding. We have to specify that, whether it's sliding or not. We're saying in this problem it is not sliding. So we can treat it with the idealization of static friction. So, first thing to do is what? Force diagram. Yeah, these problems you really should start with doing force diagrams. And how many forces are there? four forces. There's the tension, gravity. Oops, I don't want to draw it there. I want to draw it down here because it acts on the surface between the two and the normal force.
So force of gravity goes from the center?
Yes, I want you to treat gravity as though it acts on the center. And the reason for that is there's really no reason for it at this point. It's anticipating what's going to happen when we do rotation. So we'll give you the reasoning for that when we get to chapter 8. When we study rotations, we're going to apply force of gravity to the center of mass of the body. So then the reason for that will become clearer later. But you can get into the habit of drawing gravity acting on the center of the mass of the body, even if you don't quite understand why at this point. I'm not going to mark off if you put it somewhere else at this point. Okay, so now we can actually know some of the things involved. Remember this, there is no acceleration. These bodies are not accelerating, and in fact they are at rest. So there's a difference here by saying the bodies do not move. So body 1 does not move is not the same thing as saying body 1 is not moving. Do you see the difference between the two statements? Body 1 does not move and body 1 is not moving. Anybody explain why I'm making the distinction there? Yes, Ms. Swanson.
Would it be like body 1 is not moving, it isn't moving at that point, but
Yes.
it does not move, like it's like stuck, like it can't.
And doesn't move later. Right, exactly. One applies at a precise instant. It's not moving right now. Does not move is more expansive. In time, it's not going to move. So the difference here is not moving means that the velocity is 0. Does not move means that the velocity is 0 and the acceleration is 0, and there are no unbalanced forces on the body, right? So the first expression there, does not move, is more general than the second. And in this case, we are saying the bodies do not move. Neither of these bodies moves. God bless. Okay, so therefore we can say because body 1 does not move and body 2 does not move, we can say, what about these forces? Yeah, and equilibrium means all of the forces balance out in each direction. So we can say, for example, without defining a coordinate system here, you can quite easily write down that the tension balances the force of gravity on the second body, and the tension also balances the force of friction, static friction, on the first body. So therefore we can find right away that the force of static friction is equal to the weight of the second body. And the normal force is equal to the weight of the first body. So we have these two things. These are things we don't know right away: the tension, the force of static friction, and the normal force. Why don't we know the magnitude of the static friction? Static friction could be 0. Mr. Flanagan.
Because we don't know how much it's having to resist.
Yeah, we don't know at the beginning, a priori, we don't know what the tension is doing to try to get it to move. We have to find the tension before we can find what static friction is. Remember, exerts whatever force is necessary to keep it from sliding. That's what the static friction will do. Well, you don't know what else is pushing on it yet. I mean, you know generally there's tension, but you don't know yet what the magnitude of the tension is until you investigate further. Okay, so now that tells us what the force of static friction must be in order to maintain static friction. But how do we proceed here? What's the next step? Obviously, if M2 is big enough, this thing will start accelerating. It will overcome the friction. So what's missing from this? There's a limit to Fs. Right? What's the limit on the magnitude of the force of static friction?
US times normal?
Yes, sir. The force of static friction is bounded by, in magnitude, by the coefficient of static friction and the normal force. And we found the normal force here. And coefficient of static friction, remember, is just a number between 0 and 1. It's dimensionless, doesn't depend on any units. If you like, keep it in your mind, it's like 0.7 or 0.8. Sometimes for a really nice rough surface, 0.7, 0.8, it's a pretty hefty coefficient. So, and then, but this force must equal m2g, and so then we can say that m2g is going to be bounded by mu s m1g. We can cancel the g's because, without doing anything else, because g is positive. So mu2 must be less than or equal to mu s m1. So the equal sign pertains to the case where the m2 is the maximum load you can hang on there without getting acceleration. So it's a nice way of measuring mu s. You just do this really simple experiment, set it up like we've done, and just keep adding weight to what's hanging there. And at some point it'll start to accelerate, and then you know the ratio of the two masses gives you that coefficient of static friction. If mu s is less than 1, then the weight you can hang is less than the weight that's on the table. Right? The mass that you can hang is less than the mass that's resting on the table. That's what I mean when I say that mu s is less than 1. And that seems about right from your experience of things. If you set this up, you would expect you probably can't put as much mass on the thing that's hanging there as what you have on the table. That seems reasonable. Okay. What kind of, yeah, okay, so this is really simple motion, right? Doesn't move. Once it starts moving, suppose m2 exceeded that. Let's see. Let's just for a moment consider the case. Suppose it's m2 exceeded the that minimum mass, that maximum mass. Suppose m2 is larger than that, and the thing starts accelerating. Let's go back just for a minute and consider what would happen. Let's consider this apparatus again. This diagram would be the same.
It's going to be for kinetic?
Yes, that's right. So now the thing is going to be, I would indicate then a direction of sliding, right? This is sliding now in this direction. Let's do, just for grins here, the force diagram, just to see what this looks like. Force diagram on M1. What are the forces acting on M1?
You got force of friction.
Right.
It's moving.
Now it's kinetic friction. Opposes the sliding, so it's in a direction opposite to the sliding. What else?
Got all the other forces.
Normal force, gravity,
Yeah.
tension.
Right. Really, it's the same diagram, except now the static friction is replaced by Fk instead of Fs.
Well, I like the normal force. I wish it was going from gravity.
Oh, yeah, the normal force should be, I would draw it at the surface there.
That's 0.2 points off.
I said I wouldn't take any points off. All right. And then here is the other body. Okay. Now the tension in the rope is not equal to the mass, is it? Because is it accelerating? Yeah, it's accelerating now. Okay. So now we could write the acceleration of the first body is t minus Fk. And what is Fk? Mu sub k in, and n is equal to m1g because
It's on a flat surface.
yeah, all right. It does not move in the vertical direction, so we can say that it does not accelerate and it has no velocity in the vertical direction. It does not move vertically.
If they only gave us mu sub s, would we actually have to find mu sub k, or?
No, mu sub k and mu sub s are not directly related to each other. Generally, mu sub k is less than mu sub s. Just looking at different materials there are. So once you get it sliding, you don't have to push as hard on it to keep it sliding as required to get it sliding. So mu sub k is generally less than mu sub s for most materials. So you could, if you want some rough number to keep in mind, say mu sub s is 3/4 and mu sub k is 1/2. Those are kind of typical values but they vary a lot. Okay, it depends on whether you're on oil or sandpaper or what. I mean, there are a lot of different things. Okay, so let's see what I did here. I was a little quick here. I should indicate the coordinate system here. I'm going to say that they're both in the same direction. So acceleration to the right. There we go. Do it this way. There we go. On the same diagram. Acceleration to the right for the first mass is in the same direction as accelerating downward for the second mass, just so I indicate the direction of the sign here. I need to know they're both positive that way. And the accelerations will be the same now, right, because I've defined them both to be in that direction. So I have then m1a is equal to t minus mu k m1g. And the second body is going to be m2g minus t. And I've already added here by implicitly the fact that the rope has fixed length by using the same acceleration in both equations, right? Okay, now I might have to solve for t, solve for a, for t and a. All right. What's the tension in the rope? Well, you have to work it out here. Depends on mu k. And what's the acceleration? Also depends on mu k. All right, that's a nice problem to try. Real quick here, you could add these two equations together. The t's cancel, and you get m2 minus mu k m1g. So the acceleration is going to be m2 minus mu k m1 over m1 plus m2 times g. All right, that's the acceleration there. And from that, you can back out what the tension is. What kind of motion is this? Say it again a little bit louder.
Uniform linear translation.
Acceleration, isn't it? We just found the acceleration here. Yeah. Yeah. So notice that we have to have mu2 has to be greater than mu k m1 for this thing to be accelerating. And we said that m2 is greater than mu s m1 to get it broken from the static friction. And we said mu k is less than mu s. So everything's consistent here. In other words, once it starts accelerating, once it breaks free of the static friction, it will continue to accelerate. Right. Okay. This is uniform linear acceleration, and I could write down, going back to what we did just a few minutes ago, the general relationship between the position and the time from the case of uniform linear acceleration right there at the top, x of t, where the acceleration is what we just solved for. There are lots of other kinds of motion besides uniform linear translation, uniform linear acceleration. We're just doing those because they're simple and they happen a fair amount, but especially because they're easy for us. We'll be doing other kinds coming up. Okay, now let's consider the worksheet on kinetic friction. That one is a little bit simpler. We just have a body which is sliding on a surface, sandpaper. Let's say the direction of sliding is this way. Has mass m. So, first step, force diagram. How many forces acting on this body? Mr. Fanning, how many forces acting on this body?
Normal force.
Good.
Force of gravity.
Good.
Static friction.
It's sliding now.
Friction.
Kinetic friction. And which way is that going to be?
What?
Yes, sir. Okay. There is an unbalanced force acting on it, opposing the motion, so it's going to slow it down until it stops, and then it will become static, right? So everything we're doing here is only going to be valid up until it stops, and then we got to change the analysis. We got to switch over to static friction. Okay. So as long as it slides to the right, those are the forces acting on it. What is the magnitude of the normal force? Why?
Because there's no vertical change.
Yeah, it does not move in the vertical direction. If you say it that way, you cover a lot of stuff, right? Does not move in the vertical direction. It doesn't start off moving, and it doesn't accelerate in any direction. So that covers the whole thing. So the normal force does not move. And you must justify these equations. Does not move vertically. You must justify these equations. I won't accept equations just written down, a whole bunch of equations written down. That's not enough. I want to know why. Why? That's, the understanding is what makes it intelligible, right? There's nothing that causes it to move that way. So we can deduce that because we know that it doesn't move vertically. Okay. How about the force of kinetic friction? Can we write down how much that is?
You said Kn?
Yeah. It's mu Kn because it is, and I'm going to write a negative here. I'm going to write my x direction here. X is in the direction of sliding. Okay, so positive x is in the direction of sliding. Therefore, Fk is negative because it opposes the sliding. And that's equal then to minus mu Kmg. In this case, the normal force is balancing the weight. And so my equation of motion is going to be minus mu Kmg is equal to dp dt. That's Newton's second law for this problem. The left-hand side, mu K, M, and G, do those depend on time?
No.
Do they depend on where it is? No, they don't depend on anything, do they? As long as this thing doesn't, now it could be, you could imagine here it's sliding on sandpaper, and then over here at some point it slips off onto a different surface. It encounters an oil surface or something like that. That would be then, mu K might depend on where it is, right? But we're not considering that situation. It's very simple. That's a constant. Again, the force is a constant. The acceleration is a constant. Yes, ma'am, Miss Swanson.
Mu K still wouldn't depend on time even if it stopped?
So it's not, so exactly right. When it stops, it's no longer kinetic, right? And we have to stop. So we have to stop this. We can consider this only up to the point where it stops. So t has to be less than the time to stop. Once it stops, we've got to start the analysis again. We have to convert to something else. So that as long as it's sliding, the equation of motion is quite simple. Once it stops, the equation of motion is quite simple, but it's a different equation of motion. We have to consider it differently. So we have to put that on here. And in fact, we're going to find the time to stop. That's part of the problem here. So now there are lots of ways to do this. One is to go back to this generic problem here. This is the generic solution for uniform linear translation. If the force is a constant, it's uniform linear acceleration. And the position as a function of time for that case is that, where the acceleration is then the force divided by the mass. So it's, in other words, minus mu kg. So the acceleration is decelerating. And it's some fraction of the acceleration due to gravity, where mu k might be a half. So it's actually slowing down, but at a rate that is half of the acceleration of gravity. And the initial velocity is p over m, p naught over m. And the velocity, as a function of time, is v naught plus at. Okay. Now, actually, in the worksheet, I had you go about it a little different way. I wanted you to do a direct substitution. On a test, you could pull this out. Remember this. Note that it's uniform linear acceleration. The direct substitution, I said we have an equation p dot is a constant, which is minus mu kmg. And I wanted you to try v plus ct, something of this form. And so if you take the derivative of this, p dot is c, and so c must be equal to negative mu kmg. And you can get b by looking at the impetus, the momentum at time 0. We're given the initial momentum, and so b is equal to that initial momentum. And so doing it by direct substitution, we find out that it must be this. Divide by the mass, we get the velocity. T. Okay? That's the same thing that we would get by here, looking at the velocity here. This is v naught, which is p naught over m, and the acceleration is minus mu kg times time. So that gives the same answer. Okay, these things should start to become very familiar to you. Uniform linear acceleration, uniform linear translation, are really simple kinds of motion. Okay, so now how do we find the time when it stops? That is, when our analysis has got to be changed. Yes, sir, Mr. Flanagan.
Said either P of t or V of t equals 0.
Right. Yeah, let's draw this V of t. The velocity is a function of time, which looks also like the momentum plot. It's a straight line coming down, negative slope, like this. But here we got to stop here. Why can't we go past that point?
Because there's nothing to change its direction.
Yeah, it would be, if we let it go past that point, this analysis would actually say it would start moving left, turn around, right? But that doesn't work for us. And why doesn't it turn around? Well, it's because this kinetic friction stops working on it. Right when it stops, it turns to static friction. And unless there's something else going on, like the ramp is inclined, if the ramp were inclined, then it might start accelerating downward. But that's not what we're doing here, right? We haven't done that problem. So in this problem, it's going to stop, and so our analysis has to quit at this point. Cut it off there. And so we set V of t as time to stop is 0. And so time to stop is equal to P naught over mu k mg. And if you notice this actually makes a lot of sense. It's the initial momentum divided by the force that's acting, and the force is a constant. So you just divide the momentum. The force is the rate of change of momentum, so you just divide the momentum by the rate at which momentum is drained from the body, so that gives you the time. That really makes sense. You could double check these things, do a dimensional analysis on this. I want to make sure that this thing is time. So what's the dimensionality of P naught? Right. What's the dimensionality of mu k? Yeah, 1. Dimensionality of mass is m. What's the dimensionality of g?
Length over time squared.
Right, length per time squared. So this combination of P naught over mu k mg does in fact have dimensionality of t. Good. All right. That's the sort of thing I will give extra credit for if you do that on your homework or your test. Well, homework is not going to show up very much, but the test, right, is where it's going to be important. And you could check a couple of other things. If mu k increases, what if I have two different surfaces? One has got more kinetic friction than the other one. Is that going to increase or decrease the time to stop? Well, more friction means it stops quicker. So, and that makes sense here. Mu k is bigger, Ts is smaller. Okay. Now let's see. So now you have P of t, and then it's easy to the kinetic energy. If you have P of t, the kinetic energy is just P of t squared over 2m. Substitute in what P of t was. That gives you the kinetic energy. And taking the derivative of kinetic energy with respect to time is going to be P over P over m times P dot, which I get not even substituting in any particular. This would be true for any P of t, but I have a particular P of t. So, in fact, that equation does work for kinetic energy.
So that's P of t over m, or?
P of t over m?
Oh, okay.
Yeah. Using the chain rule for differentiation, I get a factor of 2 because I have p squared. And the factor of 2 cancels the 2 in the bottom. So P over t. And so this is the same thing as the velocity times P dot, which is the force. In other words, velocity times the force. So the rate of change of kinetic energy is the velocity times the force. And that's what you were to confirm. So if you plug in all these things that you have, the force is minus mu k mg, the velocity is P of t over m. All right, so now going on to the other problems, the last couple of problems, one of them actually follows onto the kinetic energy worksheet because you're to look at number 42. You have a body which is given an initial velocity and you're defined how far it travels. Well, that's very much the same. You just given the initial velocity rather than the initial momentum. You find the time to stop is independent of the mass if you fix the velocity. And that's because the force of friction is also proportional to the force of gravity, and the whole thing cancels out. I mean, the momentum, that's right. The initial momentum is proportional to the mass if the velocity is fixed, and the frictional force is proportional to the mass. Number 35, you have so-called, he calls it frictional force. Please keep in mind when he's using that word frictional, the case that he's considering is a body that's falling. And so it may be better to call it drag or air resistance. Or underwater, it would be water resistance, I guess. It's resistance to moving. So if you have something that's falling, this thing is falling this way, and you have drag acting on this. What are the forces acting on this body? You have mg, always down like that. What else?
You got that drag.
You have a drag force, so Fd. And he tells you that the force of drag is proportional to, let's say, the velocity or the square of the velocity. He tells you to assume that. Yes, sir?
Do we supposed to draw a drag from the middle?
Yeah.
Okay.
Yeah.
Drag is alpha.
What's that?
Drag is alpha.
The coefficient of drag. The drag coefficient is alpha.
I thought we used gamma.
I don't care.
Okay. That's what's so weird.
That was last week. This week I'm going to use alpha. So there's some proportionality constant. This again is an idealization. The drag sometimes, under some circumstances, is proportional to the velocity. It might be velocity squared. It could be more complicated. Okay, so, but the point is, the drag force keeps increasing. The faster it falls, the bigger the drag force. At some point, it stops accelerating, or it actually asymptotically gets there. It never quite reaches this point. But if it's moving fast enough, the drag force balances the gravity, in which case it no longer accelerates. And that's what's called terminal velocity. And you can see the terminal velocity, then the drag force is equal to the weight of gravity, the weight. And so that is the terminal velocity. And the terminal velocity is then the weight divided by the drag coefficient. Or if we're going to square it, if we're going to use velocity squared in the force law, then we have to modify this. So that's the terminal velocity. And okay. Just means that the forces are balanced. Okay, I want to look ahead a little bit to your homework for Wednesday, unless there are any questions about this homework. Homework for Wednesday. You're going to use the work energy theorem, including, and also potential energy. So, in what cases can we define a potential energy? So I'm thinking about what kinds of forces. Remember, broadly speaking, there are two kinds of forces. What are the two general categories of forces that we're considering in this chapter? Somebody other than Mr. Flanagan. Yes, Mr. Vestal.
Conservative and non-conservative.
Good. And can you give some description of those other than using the words conservative and non-conservative? Can you, in common lingo, Mr. Averett?
You say like friction.
Friction is
Non-conservative.
yeah. Also, dissipative would
So
be
it
another
doesn't
word.
give me my money back.
Never get your money back from
And
friction.
then you can say conservative. Would we say gravity?
Gravity is a conservative force. An example. Yes, sir. Good. Okay, so for conservative forces, we can define a potential energy. Because for conservative forces, the work doesn't depend on the path, but only depends on the endpoints. And therefore, we can define a potential energy. Okay, so for conservative forces only, if we have only conservative forces acting, then the path of the body moves in such a way, that the sum of kinetic and potential energies is a constant, doesn't change. And another way of expressing that is that the force on the body in one dimension is the derivative of the potential with respect to position. And we'll talk in a minute what you would do if it's more than one dimension. So in 1D. So the potential energy for gravity is what? MGH. It's just how high you are off of some reference point. So really, in this case, as far as we can consider for this particular situation with gravity near the surface of the Earth, really it's only differences in potential energy that come into play. But the question whether there's an absolute potential energy we'll leave for later. So really it's only changes in height that are important for this. So if I start with a roller coaster and I have a body here at the top, mass m, starts off from rest, rolls down here to the bottom, how much kinetic energy is it going to have here at the bottom if there's no friction, absent friction? So, yeah, no, it doesn't come to stop. So it's at rest at the top, and we give it just a little nudge so it rolls off the top, rolls all the way down to the bottom, and the height, the change in height here is h. How much kinetic energy will it have at the bottom? MGH, yeah. If it starts off with no kinetic energy, then it has kinetic energy. If it starts off with kinetic energy, then this is how much more kinetic energy has been added by rolling to the bottom.
So would it ideally go back to the same height?
Yes, sir. If this continued back up here, in the absence of friction, if it starts off here at the top, goes down to the bottom, and then comes back, it should make it back to the top, as long as it's not any higher. If it's lower, it's actually got a little bit left to get it over, a little bit of speed left to get it over. If it's higher, it's not going to make it.
If you're doing friction, would you have to include like the friction from the surface and the
Let's do friction now. Now what do we do if there's friction? So what if we have friction? Conservative forces and non-conservative forces combined. Before we do that, let's just do. What's going on?
A bunch of dudes in green suits running around.
I thought it was a dog, yeah.
They all look like Mr. Vestal? Is that what you're saying?
Oh!
No,
Hey, will you do it
I didn't see them, so I don't know. Okay. Let's suppose there are dissipative forces only, and that's pretty unusual. Dissipative only, that is non-conservative forces only. Okay? Then if we can still use the work energy theorem. Work energy theorem applies to all cases. And now the work done by the frictional forces or dissipative forces will give you, which is always negative. Dissipative forces always do negative work because they're always opposing the motion. Therefore, for the dissipative case, if I can calculate the work done by the friction, then I can tell you how much kinetic energy is lost. And so if I have going back to the previous case, if I have a block that's sliding down here, it's sliding, but there's kinetic friction, and I want to know how fast it's going at the bottom, I know how far it dropped. Oh, I'm sorry, I'm combining two problems. Hold on. No. Do it this way. Just the case of the